Physics, and today...
I'm on a skateboard. I'm going to fall. So just keep watching.
So today we're going to talk about Newton's third law of motion. We've already talked about his first law of motion, which was the law of inertia. Talked about the second law of motion, F equals ma, and now we have our third law.
So Newton's third law, you may have actually heard some of it already. It's usually stated as, for every action, there's an equal and opposite reaction. That is a good way to kind of get the idea of what Newton's third law is about, but it's also kind of confusing. And what we usually talk about is forces, or someone's walking down the hallway and decides, you know what, let's start a fight, and he punches somebody in the face. Well, that punch is an action force. There's also always a reaction force. That reaction force, if we talk about the punch, the fist hitting somebody's face, well, the face is also hitting the fist. So what happens is, if someone punches somebody else in the face with 10 newtons of force, the face also hits the fist with 10 newtons of force. The question always becomes then, well, how come they don't cancel each other? How come that person does get hurt where the fist doesn't really hurt that much?
So for that, we would have to draw some free body diagrams and look at what's going on. Okay, so instead of being super violent and talking about a fight, let's talk about me pushing Sofia out of the frame. So I pushed him out of the frame, and then he pushed himself back in.
Almost.
And let's talk about a free body diagram. Now, if you remember, when we did a free body diagram, we were talking about one object. Right? So this is going to be Becker, and then we'll have another free body diagram for Peter Sack. So,
I'm bigger than her.
So, on my free body diagram, first of all, I'm standing on the floor. So we should know that I have to have a force of gravity acting down, and the floor is supporting me. So I have my normal force acting up. Mr. Petersack has the same forces acting on him. Okay? He's standing on a skateboard, so he has his force of gravity acting down, and the skateboard providing a normal force, which is acting back up.
Now remember, length of arrows is also kind of proportionate to their strength or their magnitude. So I drew mine a little bit longer than her arrows there because I have more mass than her, and therefore my force of gravity will be greater than hers.
So next we have to think about my pushing Mr. Petersack. So let's start with his free body diagram. Okay? If I'm pushing him, there's a force acting on him. So we can add in that force to the right, my applied force, trying to push him off of the skateboard.
So Newton's third law says for every action is an equal and opposite reaction. So if she pushed me, well, I also pushed her. How then did I move? How does anything move in this case? Well, her force acts on me. She's pushing me, so her force is applied to me. The force that I automatically pushed back with her on pushes back on her. So I move in this case because I was on a low friction surface. So in that case, when she pushes me, I move. Now, she did push me with a certain amount of force, and I naturally pushed back with a certain amount of force, the same amount. How come she didn't move back?
So I was standing on the floor. So I had a lot more friction between my shoes and the floor than Mr. Petersack had between the wheels of the skateboard and the floor. So I had that friction acting to balance it out. And it was probably, I moved a little bit.
Now, my inertia caused her to move back just a little bit during the push. She started with her hand or her arm probably kind of half bent, and when she extended, her body would go back a little bit as I started to move away. But who moves more? I move more because I'm on a low friction surface. If she was to try it again, while I'm not on that low friction surface, I don't move as much. Why? Because now also I would have a friction force.
Now when we're talking about those equal and opposite reactions, let's look at our diagrams and see where those forces are. Okay? So our equal and opposite reactions, we were talking about the action being me pushing Mr. Petersack with an applied force. And the reaction is the applied force that he then pushes back on me. Notice how those are on different free body diagrams. But those are the ones that are giving that equal and opposite reaction.
So the opposite part has to do with the direction. So this direction here is opposite that direction. The equal part means that they have the same exact magnitude.
Okay, so I tried to draw our lengths as close as we could to being the same magnitude.
So if this was 10 newtons of force, hers would also have to be 10 newtons of force.
Okay, so that's Newton's third law in a nutshell. We're going to do a lab where we'll get to explore it a little bit more with balloons, so that should be fun, and see where those forces are coming from. But remember that the equal and opposite forces are going to be on different free body diagrams. Okay, that will always be the case, because we only do one object within our free body diagram.
Now, the Regents questions that have to do with Newton's third law are simple questions to answer as long as you recognize that it's a Newton's third law question. For example, a question that comes to mind is a baseball being thrown in a baseball game, and a batter hits that baseball, and they say, well, the bat hits the baseball with 100 newtons of force. How much does the baseball then apply to the bat? The question basically tells you it's a Newton's third law question by saying baseball, bat, bat, baseball. Just the same exact two objects in contact. If the bat hit the ball with 100 newtons, how much did the ball hit the bat with?
Okay, you should recognize that's our equal and opposite force, so they should be the same. All right, any questions that you guys have, please ask. We're going to do a lab with this, and then we're going to test on all of Newton's laws on Thursday. So keep up with all of the other ones and ask questions when you have them.
Extra help is always available, and also, while we're here, you should be buying a review book, $15. The check is due by 10/13, October 13th. And as always, have a great night.